Hey guys, we're on to module 4 now, where we talk about rational functions, properties of rational functions, and characteristics of rational functions. And the best way to have that discussion is with a visual of the graph of a rational function. So I want to take this example 0, as I've titled it, to give just a quick introduction to the characteristics of the graph of a rational function, with the simplest of rational functions, one of our toolkit functions, the reciprocal function. Let's see how many times I can say the word function in a single video. Let's see. So we're going to sketch a graph of the function f of x equals 1 over x, that reciprocal function. And I realize we have it on our handout of toolkit functions. But I want to kind of think through, especially since we're going to have to extend this idea to more fractions and rational functions throughout the examples in Module 4. I want to kind of break it down and see how does this graph of 1 over x take shape, literally. So here, what we're going to look at with this first rational function, which is just the simplest 1 numerator and x denominator. We first of all, so we're going to start a sketch. To start a sketch of the graph, a good place to start would be points on the graph. So let's start with a couple of points, real simple points. When we plug in 1 for x, then the y value would be 1 over 1, which is 1. Or if we plug in -1 for x, then the y value would be 1 over -1, which is -1. So we've got the points 1, 1, and -1, -1. Let's just throw those up on a sketch of the graph. We need more work from there. So what we're going to do, what we could do, and what a textbook, and our textbook usually does, which is perfectly good, is plug in more x values and start to put dots on the graph and connect the dots. And there is absolutely nothing wrong with that. In fact, that's a great way to think about it. I want to give you a little bit of an alternate way to think about it here, the way that makes sense to me, which is if we start plugging in different values of x in particular, as x grows larger, when we plug in an x value of 2 or 3 or 4 or 5, the fraction 1 over x would be 1 over 2, 1 over 3, 1 over 4, 1 over 5. It gets smaller. Those fractions get smaller and smaller, growing closer to a y value of 0. So we have this kind of curve, this piece of the curve from that point 1, 1. As x gets larger, as we move to the right, the y values are getting closer and closer to 0. So we have this piece of this branch of the curve of our function. And if we follow a similar argument, same thing happens to y values on the negative side of the graph. If I plug in -2 for x, -3, -4, -5, then I have fractions that are getting smaller and smaller, closer and closer to 0 on the negative side. This gives us a horizontal line. The curve approaches the x-axis, the line y equals 0. And we note that this horizontal line, it's called a horizontal asymptote of the graph. So that horizontal asymptote is a line that the graph approaches, the curve approaches toward the ends of the graph. That's starting to shape up now, the curve of the graph that we're looking at, the branches of the graph. Speaking of lines that the graph is approaching, though, we got another one. Note the domain restriction. X cannot be 0 because we can't divide by 0. The curve will approach an x value of 0 but never reach it. And the line x equals 0, which I've drawn in orange here, is a vertical asymptote of the function. So the curves that we've started now are going to continue and approach that vertical asymptote of x equals 0. And I'll show that now. I'm not going to run the math of it on this slide, but it can be confirmed that as x gets smaller, closer to 0, the y values grow larger. And so if I plug in like an x value of 1/2 or 1/3 or 1/10, then we get larger and larger y values, and we get this curve that's approaching the orange vertical asymptote, but never quite reaching it, and just continuing up in the positive direction forever. Similarly and symmetrically, on the opposite side of the axis in the negative direction, same thing happens, and this completes the branches of the graph and the sketch of the graph of this 1/x function. So some characteristics that we pay attention to here are, well, we always like to start with some points on the graph, but then we recognize that the curves of a rational function are going to depend on and kind of revolve around the asymptotes, horizontal asymptotes, vertical asymptotes of the graph. So a lot of the work that we do in sketching graphs of rational functions and a lot of the characteristics that we talk about with graphs of rational functions center around where are the asymptotes? Where are the asymptotes? Where are some points on the function? Where are the asymptotes of the function? And we sketch the graph around and approaching through those points and approaching those asymptotes. And we'll see that as we go through the examples in this module. One last thing. A good one to be familiar with, another good simple example to be familiar with is 1/x squared, which is basically the same picture, except with hopefully an obvious difference here. Both of the curves of this graph are above the axis. Both of the curves of this graph are on the positive y side, and that's because we're squaring the x value. Anytime we square x, we get a positive answer. So we have two branches, both on the positive side of the axis for 1/x squared. That'll come into play occasionally when we are graphing rational functions throughout this module.